Hello everyone, good evening. My name is Marcus Collier-Wright. I'm co-founder and CTO of NeutronStarSystems, and with us, the future is electric. The problem that we are solving today is that current propulsion systems are not meeting their customers' needs. They are limited in their power and operational ranges, and they rely on expensive and rare propellants. This means that they can't be optimized to customer solutions, and the full potential of missions remains inaccessible. Our solution is Supreme, a next-generation electric propulsion technology. We combine two key technologies: applied field magnetoplasmodynamic MPD thrusters and industrially mature high-temperature superconductors. This combination results in a propulsion system which is scalable, efficient, and can run on alternative propellants. We provide flexibility, versatility, and customizability to our customers, and this allows us to optimize our solutions and reduce their costs. So where do we stack up against the competition? Well, to evaluate this, we've taken two key metrics: efficiency and speed, or thrust. So Hall effect thrusters are a status quo system which provide a high thrust at a relatively low efficiency. And on the other hand, gridded iron thrusters provide a much higher efficiency at the cost of a lower thrust. With Supreme, we can offer both. We can offer you high efficiency, we can offer you high thrust. We can offer whatever the customer demands. This is thanks to our 5 key competitive advantages. We have a wide propellant flexibility, allowing us to operate on propellants like argon and ammonia, which are 2 orders of magnitude cheaper than the existing status quo xenon. This also opens up new possibilities for hybrid chemical electric propulsion systems, which are much simpler and cheaper than existing systems. Our technology is simple, it's robust, and it's reliable. It's based on over 60 years of research heritage in 6 different countries around the world. It's a scalable technology. We can go up to higher powers with minimal mass and volume penalties, and in fact, we can scale this technology over a wider range of power classes than any of our competitors. And finally, it's throttleable. This means we can operate over a wide range of conditions, making us suitable to almost any mission application, and allowing us to optimize thrust performance for certain orbital maneuvers, thus cutting propellant consumption and gaining cost savings. There it is. So, these competitive advantages form the basis of our vision, and this is built on a wide application of different mission scenarios. Our main market entry points are providing propulsion for small satellites and constellations and geocommunications platforms, whilst we also see that we can enable multi-use servicing vehicles for applications like debris removal and decommissioning, orbit raising, satellite refueling, and satellite maintenance. Now, if we look further ahead, we see that our technology can establish a lunar-based economy, first based on lunar gateway logistics, followed by lunar servicing missions and lunar cargo transfers. And even further ahead to the future, we can enable Mars missions, such as cargo missions to Mars, crewed Mars flights using electric propulsion, and the establishment of a Mars gateway, all the while supported by science and exploration missions and asteroid mining markets. In short, we see that our technology can enable this next generation of space missions. To put this into some context, we've evaluated the opportunity on offer here. We see all of these mission applications entering the market on regular intervals as a direct consequence of our technology coming to the market. This is the opportunity that can be captured. We're predicting annual revenues of over 500 million euros by the year 2038. Our technology can make the market. We have the team to capitalize on this opportunity. Our core management team combines over 80 years of industrial experience on a wide range of topics, including superconductors, spacecraft systems engineering, electric propulsion, and project management. Our technology expert, Professor Georg Herdrich, is the leading authority in Europe on MPD technology, and he's overseen the production and testing of the most advanced MPD prototype anywhere in the world. And to support us, we have assembled a young, dynamic, diverse, multicultural, and motivated team. They've worked together for over 2 years, they have a fantastic chemistry, well-defined roles, and they give us the ability, the flexibility, and the determination to overcome any challenges we are faced with. Today, we're looking for seed funding of 1.6 million euros to operate for the first 18 months of our company operation. And in this time, we will secure 3 key milestones. Firstly, the development of a 5-kilowatt demonstrator using superconductors. Secondly, the securing of key intellectual property. And thirdly, and most importantly, the closing of commercial deals with our key customers, including Sierra Nevada Corporation and Northrop Grumman. We believe that we have a very special opportunity here to do something unique with this technology. If you want to join us on this adventure, or you're interested to find out more, we'd love to speak with you. You can find us at the rest of the event or get in touch with us over phone or email. Thank you very much for listening, and I look forward to taking your questions.
How does the cost of your solution compare to competitors?
We've done some costing models based on a paper published from the NASA Jet Propulsion Laboratory, and the conclusion we come to is that we're cost competitive in terms of the unit cost and the development and qualification costs with the data that we have available on our competitors.
In your comparison table of the different propulsion systems, you don't put the chemical propulsions for the comparison. What is the reason?
I mean, chemical is a whole different class of propulsion to electric systems. They simply cannot reach the same level of mass utilization efficiency as electric systems. Chemical is not a competitor for us because we're operating two completely different regimes.
Okay, thanks.
When do you expect to fly your first prototype?
Yeah, we expect to reach flight proficiency by 2024.
Any other questions?
How do you expect to solve the problem of power sources for high-power missions?
As you saw with some of the presentations earlier today, there's a lot of exciting technologies which can really bring down the weight of solar arrays, for example. And what we see is that the limitation to going to higher power classes has really been that the thrusters are not available. If you want to go to higher power classes at the moment, you have to cluster lots of small units. This adds a lot of complexity and mass, and that's a lot of extra challenges for the systems engineering. We can go to higher power classes at a much more efficient mass, avoid clustering, and come with single units to deal with this problem.